things. So a relation is just any relationship between numbers. So every equation is a relation. Every expression is a relation. Just it's any kind of relationship. But functions are special. Functions are special relations. And what's special about a function is each element in the domain only goes to one element in the range. And we'll talk a little bit about domain and range in just a second. But what that means is that if I take, the domain elements are the numbers that you plug in to the relationship. If I plug in a number, say 2, I plug in a 2, I only get one number out. That makes it a function. If it's not a function, I could plug in a 2 and I could get 2 or 3 numbers out. But with a function, you plug in a number, you plug in one number, you get one number out. And there are different kinds of functions. We have functions that are called one-to-one. Okay. And if this is your domain and this is your range, and I have some numbers in the domain, and I have some letters in the range, one-to-one means that basically every domain element is used. Okay. So if I plug in a 1, I would get a D, 2 would give me a B, maybe 3 would give me an A. But all 3 of these would be used. Then you have something called onto. Oh, and one-to-one you can write it like this also. You don't have to write out the words. Okay. Onto is every range element is used. So if I have my domain and I have my range, and 1 might go to A, 2 and 3 might go to B, and 4 might go to C. This is okay, it's still a function, because when I plug in individual numbers, only when I plug in a 2, a B comes out. So 1 goes in, 1 comes out. If I plug in a 3, a B comes out. That's still okay, that's still a function. But all of my range elements are being used. And then when you have both has a B first. So it's one-to-one and onto. So that happens when every range element, domain element goes to exactly one range element and all are used. So again, this is my domain and this is my range. Basically what I'm saying in this case is I have the exact same number in both, the same number of numbers, and each set they're paired off individually. I'm sorry, and also on one-to-one, every element is used only once. So in one-to-one, every domain element is used, and you get to one element in the range. In onto, every range element is used. And in one-to-one and onto, you get every element is used in both the domain and the range, and they're pairing exactly one-to-one of each. You'll notice that never do I have more than one arrow coming off of a domain. That's because to make it a function, each one of these elements can only go to one number. So let's talk about domains. Domain is the input value or variable. We usually use x's, so domain is usually your x's. And so it's the input value. So domain are the numbers that you plug in. And range is the output values. And those are usually your y's. If we were using A's and B's, the domain would be the A's, the range would be the B's. Yeah.
So, like, you said usually, what would be?
Well, because sometimes we use different letters.
Okay.
Just like, it's always alphabetical though.
Yeah.
So if you were using P and Q, let's just say, then this would be P and this would be Q. So it's usually X and it's usually Y. Those are the most common ones we use, but sometimes we throw different letters in there. So naming domain and range. The domain is the X's. So I go through, and for my domain, I'm just going to list the X's. So I have -6, -5, -3, -1, and +6. And my range, that's all the y's. So I have -1, -9, -7, +7, and then -9 again. But I only list each one time. So I don't list that -9 a second time. Now, to tell if it's one-to-one, onto, both, or neither, and to determine if it's a function, sometimes it's easier to do what's called a mapping. And to do a mapping, that's where we list our elements, +7, like this, and we draw, like here's the domain, here's the range. And we can draw arrows to talk about the pairings. So -6 and -1 were a pair. -5 and -9 are a pair. -3 and -7 are a pair. 1 and 7, and then 6 and -9. So the arrows represent all of your ordered pairs. Now to tell if it's a function or not, as long as this side has only one arrow each. Okay, so basically your x's can only be used one time. I can't have like 5 also go to -1. Yeah.
How come 6 goes to -9 too?
Here I had -5, -9, and 6, -9.
Oh, okay.
Yeah, you don't write it twice because it's the same number. So you write each number one time. So each one of these, I look and I go, okay, 1 arrow, 1 arrow, 1, 1, 1, I'm good. So it is a function. As long as only 1 arrow, we're good. We have a function. And then what I do is I look and I see that I don't have, to be one-to-one and onto, so both, you have to have like 1 arrow going to one, like each side has to have only 1. I don't have that here. But what I do have is each one of these are being used, and each one of these are being used, but see how this has 2 arrows? That looks like this. So what I have is it's a function and it's onto. So you don't have to rewrite them, but we will put them in a mapping so that we can tell if it's a function and what kind of function it is. So I have 2, -1, -2, -1, and +2. So I only list those one time each. And for my range, I have -2, -1, 0, 1, and 2. Okay. So 2 and -2 go together. -1 and -1. -2 and 0. And then -1 and +1. And then 2 and 2. Okay?
So why can't we write the number? Is it like against the rules to write the numbers again?
Yeah, because what this is this is representing a set. This box or bubble or whatever you want to call it, this represents a set. And if I write these numbers twice, they're the same number. So each number, even if it's being used more than once, it's in the set only one time. And if I write it again, like if I wrote another -1 and then another 2, then I would maybe draw 1 arrow off of each. And see how this has 2 arrows and this has 2 arrows? This is not a function. But if I drew 2 and -1 again and drew different arrows, I would go, oh, they all have 1 arrow, and I would say it was a function, but it's not, because the numbers are being used more than one time, and in a function, x's can only be used one time. So this is not a function. And since it's not a function, it can't be one-to-one or onto or any of that. Now, let's say I have, not x, sorry, oops, wrong button. Let's say I have some set, this is just another example, and I have 2, 1, 3, -4, and then I just list 2 and 1 again. This is still a function, even though I've listed the 2 twice, it's still the same pair. I just listed it twice. So the x can show up twice in the row if it has the same y. Does that make sense? Then this is still a function. It's when the x shows up twice and has 2 different y's that it's not a function.
So the x can show up repeats.
Looking at a graph to tell if something's a function or not. I've got all these points. This x right here, -2, this x has 2 y's. Do you see that? So I could do this whole thing and I could find the coordinate pairs and I could make the domain range mapping, but because I have 2 y's on the same x line, it's not a function. So I don't have to do all the rest of it. And here the mapping is already done for us, but we want to double check and make sure it's done correctly. So you just go through and you make sure that none of these are repeated and that none of these are repeated, which they're not. So then I look at this and I say, okay, each one of these only has 1 arrow, so yes, it's a function. And that's because there's 1 arrow each. And it is not 1-to-1 because I have 2 arrows coming here. It's also not onto because you see how I have this extra 8 hanging out? And to be onto, all of the range has to be used. So it's not either. It's not 1-to-1, it's not onto, it's neither. And that's because, so this tells me not 1-to-1. And this extra guy tells me not onto. relations can be discrete or continuous. Discrete means it's sets of individual points. And they do not run together, do not connect or run together. Okay, things that would be discrete would be the number of jelly beans in a jar. Okay, because if I take jelly beans out, if I take 5 out, it's 5 less. It doesn't like gradually become 5 less, right? Like I'm not taking out microscopic parts of jelly beans as I go. I'm taking out whole jelly beans. Continuous are numbers that run together. So it's a gradual change. Things that are continuous, changes in temperature are continuous. It may happen quickly, but it's not 20 degrees this second, and the very next second it's 90 degrees, right? But no, it happened fast, but you went through all the different degrees. I mean, the temperature went down, or it came up, but it happens over time. Time is continuous. Time happens, it runs into each other. Growth. When you're growing, you don't go to bed one night and you're 4 feet and you wake up the next morning and you're 5 feet. It runs together. So those are continuous. So in a graph,
I have a question.
yeah.
How do you get your jelly bean?
If I have jelly beans in a jar and I take jelly beans out, if there's 20 in there now and I take one out, there's 19. If I take another one out, there's 18. There's not like 20.999, or 18 point. Does that make sense?
Yeah.
It's like whole separate things. They don't blend together. So on a graph, a discrete relation is a set of points. It's just points graphed on. They don't connect. And a continuous relationship would be a line or, a curve, but they run together. You connect them. And so these are things that happen gradually. These are things that are set individual. Okay. Vertical line test is a nice way to test a graph for being a function. And the way it works is if you take a vertical line like this guy, that's a vertical line straight up and down, can only hit the graph one place at a time. So I could have some weird funky looking line like that. Just draw some weird funky looking line. Or I could have something like this, maybe. Okay. If I take this vertical line and as I move it across my paper, do you see how it's only touching that blue line once in one spot? So this is a function. Oops, I'm moving the wrong thing. But when I come over here, it's touching it in 2 spots. So 1 spot okay, 2 spots not okay. So this is a function, not a function. So you can take your pencil, ruler, imaginary line inside your head, and if you move it across the graph, if it touches that picture of the graph in more than one place at a time, it's not a function. Which, if I take us back for just 1 second, remember this where it had 2 y's? that would not pass the vertical line test, because if I put a vertical line through here, it's going to touch those 2 points at the same time. That's why that works. So, okay, so the Tour de France. It's not the same length every year, which I think is interesting. But so 1998 to 2006, these are all the different lengths that the Tour de France was. Is this discrete or continuous? It's going to be discrete. And the reason it's discrete is you would not connect the lines. It's not, you know, there's no race in 2000 halfway through that's somewhere in the middle here. Right? These are individual races with individual lengths. Does it represent a function? Well, if we take a vertical line and we draw vertical lines through all these points, it's not touching anything more than once. So, yes, it's a function. Which makes sense if you think about it. They're not going to have 2 Tour de France's in 2002, right? That's silly. Graphing. I need a refresher. This is my y-intercept. And this is my slope. And this is in the form of y equals mx plus b. So to graph this, I'm going to start at my y-intercept, which is -3, so that's right here. I'm going to put a point right there. So this is my start. And this is my directions. And it's rise over run. And if it's positive, you go up, and if it's negative, you go down and then to the right. So it's +1 over 2, so I'm going to go up 1 over 2. And I can keep doing that if I want to, till I get a bunch of points. And then I'm going to connect the dots. Now, is this a function? Yes. It is a function because it will pass the vertical line test. Is it one-to-one onto both or neither? Now, when we're looking at a graph, it's not as easy as a mapping necessarily, but if we continue this graph out into foreverness, you know, into infinity, this line is going to stretch continually, gradually increasing over time. And over here it's going to continually decrease over time. So eventually I'm going to go right and left forever. So I'm going to hit all the positive and negative x's. And I'm going to go up and down forever. So I'll hit all of the negative y's. So this line is both. Because I'm only getting 1x to 1y. And it's onto. Right, so this x only has 1y, this x only has 1y, etc. And then it'll go on forever. So I'm going to hit every negative and every positive number in both the x and the y.
Could you show an example of when it would only be like 1-to-1?
Yes, a parabola. No, sorry, that's not 1-to-1. That's...
You can do it either one.
not a parabola, this would be 1-to-1. So if you graph, sorry, if you graph y equals the square root of x and make it a function, So I'm going to only graph the function part. I get a graph that looks like this. And so this would be 1 to 1, but not onto, because I'm not getting any of
Okay.
this. I'm not getting any of the negative x's. I'm not getting any of the negative y's. Does that make sense? Okay. If I don't force it to be a function, it comes down like this. So we can limit the graph and make it a function. Now one that is neither would be a parabola. Like this is neither 1 to 1 nor onto. It's still a function. It passes the vertical line test, but I'm not getting everything. Right? I'm not going to get any of the negative y's. I'm not getting any of these x's. Or I'll get all the x's. I'm just not getting all these y's. So. And we have a line. It's connected, right? So it's continuous. Basically, any line or curve that goes on forever is going to be continuous. Erase that guy. Go ahead and erase that guy. Okay. We have an independent variable and a dependent variable. The independent variable is called the independent variable because it can be, any number can be picked. This is the domain. So it's our x's. And the reason we do that is because I can pick any x and I can throw it in. That's the independent variable. Our dependent variable is the variable, the value that comes out. What's the word I'm looking for? Oh, it should be revealed. It's not the right word, but that's okay. Okay, so basically this is called the dependent variable because it depends on which number I picked and put into the equation, right? So if I pick a 2, it'll give me a different answer than if I pick a 6. This is my range, so these are my y's. Okay. An example of that would be if I had a function for how much money I spent at the candy store. So if I said money is equal to, not money, but, okay, we'll say y is the total cost. X is the pounds of candy. Right? So I'd be like y equals, let's just say every pound of candy is $1.50. Okay. So how much money I spend at the store depends on how many pounds of candy I buy, right? So if I buy 1 pound of candy, I've spent $1.50. If I buy 10 pounds of candy, I have spent $15, right? So X is be independent because I can choose how many pounds of candy I buy. But Y is dependent because the total cost depends on that choice. Function notation. Function notation is only used for functions. And so if you see this, you know for a fact you have a function. And so what happens is y is replaced by f of x. This is called f of x. And what this says is this is basically when you see f of x, it's saying this equation is a function of the variable x. Also, you might see g of x, h of x. This just means different functions. Like if you have a problem with more than one function in it, that's so you know the difference between the two. So when we use function notation, so I'm given f of x is equal to 2x squared minus 8. Basically, this is the same thing as y equals 2x squared minus 8. That's what this means. Or if g of x is equal to 0.5 x squared minus 5x plus 3.5, that's the same thing as y equals 0.5 x squared minus 5x plus 3.5. So they're the same. It's just this notation is really useful. And here's what it's really useful for. If I have f of x is this, and I want to find out what's f of 6.
I don't understand what you're doing now.
But that's useful. So I have f of x is 2x squared minus 8. If I give you something in the parentheses here, this, what's in the parentheses, replaces x. So instead of having 2x squared minus 8, if I want to do f of 6, that's 2 times 6 squared minus 8. So I just take whatever's in that parenthesis and I plug it in for the x instead. And anything can be in the parenthesis. It can be a number, it can be a variable, it can be both. It can be an expression. So whatever's in the parenthesis, I take the x out and I put what's in the parenthesis in. And so then from there, I evaluate it. So 36 squared is 36. And then 2 times 36 is 72. And then 72 minus 8 is 64. So like I said, you can plug in things other than x, or I mean the number. So f of 2y. It was 2x squared. Now it's 2 times 2y squared minus 8. So I took that x out and I put 2y in. And then I have to square the 2y. So that's 4y squared. And then I multiply that by 2. And then I can't do anything else to it. So I'm done.
You just squared it and put the square back
Hmm?
on. You just squared that and put the square back on.
Well, I squared the 2, right? And that gave me the 4. And then y squared is just y squared. Does that make sense?
But then it comes back down in the...
It's still there because I don't know what it is. So if I put a square on a variable, it just hangs out because I don't actually know what y squared equals, right? Because I don't know what I don't know what number y is.
So some of them come out as
Yes.
numbers and some of them come out.
Yeah. So we'll do this one again with the 4a because that's why I crossed out the one with the number because I think the ones with the variables are more challenging. So this one though is g of 4a. So g of x is that 0.5 x squared plus minus 5x plus 3.5. Sorry to make that so squishy. So instead of x, I'm going to put 4a. So g of 4a is going to be 0.5 times 4a, and then that's squared, minus 5 times 4a minus 3.5. So now when I square the 4a, oops, getting ahead of myself and writing down the wrong number. 4 squared is 16, a squared is just a squared. So the 4 squared became 16, and the a becomes a squared, not equals, minus 5 times 4 is 20,
Where'd you get
a.
16?
4 squared, I took this squared, right? And I have to square the 4 and the a. And then 3.5 just hangs out. And then I have to do 0.5 times 16, so that's 8 a squared minus 20a minus 3.5. Okay, so linear equations make a straight line. So in order to make a straight line, you can have fractions as long as there's only numbers in the denominator. You cannot have any variables in the denominator. You cannot have any exponents on variables. You could have 2 squared, that's fine, but you can't have x squared. You cannot have any variables times variables. So you can have variables and numbers multiplied together all day, but you cannot have like x times z or x times y. That can't happen.
Where's this in the variables gonna get?
Under a radical. Here. Or no, down up here in denominator. I just didn't write it all the way out, sorry.
And what if it's like 1x times 2x? Okay.
That's okay. No, that's not okay, sorry. No, because when you multiply the x's, you'll get x squared. Yeah, you could have 1x times 2, just not times 2x. And you can't have any variables under a radical. So a linear equation, kind of, they look boring. They look like this. They can have just a letter and a number. They can have fractions, just not with a variable in the denominator. Those are fine. Those are all linear. Nonlinear equations. Exponent on a variable, not okay. Variable under a square root, not okay. Two variables being multiplied together, not okay. Variable in the denominator, not okay. So this is fine, this is not fine. And a linear function is a linear equation y equals mx plus b. Now I could turn any one of these into this, and m and b are real numbers. Okay, I could turn any one of these into this format. I could not make any of these look like this. Now the only linear equation that are not functions x equals some number is not a function. So this right here, not a function. These are all functions. This is not, and the reason is because if x equals a number, it's a vertical line. And vertical lines definitely do not pass the vertical line test. Because if you put a vertical line on top of a vertical line, it is touching an infinite number of points. If things are linear functions or not. We just look at the variables. We have an x by itself, nothing weird happening to it, so yes. X in the denominator. No. No x's in denominators. That's bad. 3xy, not a function. We don't want any xy action going on. Okay. 5 over x plus 6, no. No x's in the denominator. But negative 3/2 x plus 1/3, sure, that's okay. The growth rate of a sample of Bermuda grass was given by the function f of x is equal to 5.9x plus 3.25, where f of x is the total height of the grass. After x days. So how tall is the grass after 3 days? Well, that would be finding f of 3. So I'm going to put in a 3. And I'm going to cheat and get the calculator. So after 3 days, this grass would be 20 inches tall. So at the end of 3 days, it's 20.95 inches, and 3.25 represents the initial height of the grass. So how many times longer is it after 3 days? Well, to figure out how many times longer it is, we take the new height, right? And we divide it by the original height. So we do 20.95 divided by 3.25, and it is 6.4 times longer. And if we want to find out how many days until it's 50 inches tall,
Did you say 6.24?
so no, 6.4. I'm going to plug this in for f of x because f of x is the total height, and then I'm going to solve for x. So put x, leave the x in there, 3.25. So I will subtract 3.25 from both sides.
Where'd you get the 15?
Right here. Backspace. 47.2 is equal to 5.9x. So then I'll divide both sides by 5.9. So after only 8 days, our grass would be 50 inches tall. Standard form is AX plus BY equals C, where A, B, and C are integers, and A is positive. That is the standard form of the equation, and the whole point is it looks pretty. We want to make these look pretty, so we're going to put them in standard form. Okay, so the first thing I need to do is I need this y to be on the same side as the x. So I'm going to move it over here. And if I move it from one side of the equal to the other, I change the sign. Or if you want, you can think of it as subtracting it from both sides, however makes more sense to you. So basically, I subtracted 8y from both sides. Okay, the next thing I need to do is I have to get rid of that. Okay, we cannot have denominators. Everything has to be an integer. So I'm going to take everything and I'm going to multiply it all by 10. And the reason I did that is because when I multiply this by 10, the 10s will cancel, and I get negative 3x. Minus 80y equals negative 150. But this first number has to be positive, so I have to get rid of this. So to do that, I change all signs. So it becomes 3x plus 80y equals 150. Now they were all negative, so they all became positive. If some of them had been positive, I would have made them negative.
Did you say all the numbers have to be positive? Or?
No, just this first term has to be positive.
Okay.
So because this one was negative, I changed all the signs. If it just happened that they were all negative, so, but if this, let's say this 150 had been positive, it would now be negative.
Okay.
And what if it was a regular positive 80?
If it had been a positive 80 here, then it would now be negative. Yeah, and if this had been positive, this 3 was already positive, then I wouldn't have had to do anything. It's just that first number that needs to be positive. Again, because we're trying to make it look pretty, and it looks prettier if the first number's positive. Because, yeah. Sometimes it's very simple. 3x minus 6y minus 9. I have to take this and I move it. Because I want my number to be alone on the other side. So I do 3x minus 6y equals 9. This is already positive. They're already all integers. So I'm done. When we use this method, the best time to use this method is when A and B divide evenly into C. Okay. So in this case, when I put this in standard form, I get that. 2 goes into 10 and 5 goes into 10, so that makes this a nice equation to graph with intercepts. And so what I do is I take 2x and I make it 10, and I take 5y equal to 10. So essentially I take away the 5y on one and I take away the 2x on the other. In other words, I plugged in 0 for y, and then I plugged in 0 for x. Okay, so then I divide by 2 over here, and I get x is equal to 5. And I divide by 5 here, and I get y is equal to 2. These are the points. This is the x-intercept. So this is where the line hits the x-axis. This is the y-intercept. So it's where the line hits the y-axis. So I go over to my x-axis and I count to 5. And I put a dot. And my y-axis and I count to 2 and I put a dot. And then I connect the dots. Okay, so the 2 does divide evenly into 8, but the 3y, negative 3y, and if I divide both sides by negative 3, I get y equals 8/3. Not quite as pretty. And this is about 2 2/3, not about, it is exactly 2 2/3. So I go to my x-axis and I go to negative 4 and I put a dot. And I go to my y-axis and I go to 2 2/3-ish and I put a dot. And then I connect the dots.
Would it be the same if we just divided 8 by 3? Would I still get the same answer?
Yeah, you get 2.333333, or 6, no, sorry, 2.6 is forever. Yeah,
You
so.
can put it in decimal form.
Yeah, you can put it in decimal form. But in any case, it's somewhere between the 2 and the 3, so it's not as nice. You can still do it, it's just not as nice. Once we get into other forms of graphing, when we're using y-intercepts and things like that, well, in this case, the y-intercept is not great either, but when we get into other forms of graphing, there are other methods that will be nicer because you'll get nice whole numbers to graph.